Okay, we've been talking about the frequency scan measurement in the EMI receiver application. Now let's move on and talk about the other measurement in the EMI receiver application, which is the strip chart measurement. Now the strip chart measurement uses the same meter display as is used in the frequency scan measurement, and it's controlled in the same way under the mode setup meters control key. But in the strip chart measurement, instead of looking at a spectrum, you're looking at a time record of the instantaneous voltage values on up to 3 detectors. So here you can see I've got a signal that's pretty active, and you can see the pulse nature of the signal in the using the peak detector, and you can see when the signal comes and goes using the quasi peak and the EMI average detectors. So I'm getting a clearer picture of the dynamics of this signal, uh, more or less in the time domain. Now with the meters controls, I can do things like set limits. So each of the meters has a limit that I can set, so I can turn the limit on for meter 2, say, and then drop it below a certain level. So anytime the meter crosses that level, the bar turns red and the trace turns red, and I can set a different limit for each of the 3 meters. So that's one way of being able to tell when a signal crosses a certain limit. And also, I can actually capture data for up to 20 minutes using the strip chart. So you can use the limits function basically to detect changes in the meters based on values that you set yourself. Now you can see that I'm only able to see 10 seconds of data right now given the current display settings, but I can actually capture data for up to 20 minutes. If you go to the X scale control, you can set the maximum duration. It defaults to 500 seconds, but I can set it up to 1200 seconds or 20 minutes. And I can actually look at all of the data that I've captured for that up to that whole 500 seconds. So if I stop the meter display and then adjust the reference values, say, it'll basically let me scroll through the display, and I can look at the past data that's been captured already. And if I adjust the scale per division, I can compress it or expand the data and see basically everything that I've already captured. I can use markers in this display. I can either use the marker to determine the duration of an event, for example, by moving the marker to, let's say, the edge of this event here. Say there, and then do a delta and move the marker to the edge of this event here, and it's telling me that this event is about a 430 millisecond event. Or I can actually look at the delta between 2 detectors by doing a delta marker from trace 1 and then moving the marker to trace 2, and now this is telling me that the delta between trace 1 and trace 2, in other words, between the peak detector and the quasi-peak detector, is 8.5 dB. And by coupling the markers together here and then moving them together, I can move across the entire record and take a look at the peak to quasi-peak ratio across the whole time that I've been capturing. So with the strip chart, you're able to get a lot more insight into what's going on in the time domain. And I should emphasize that this capture is gapless, that we hold off alignments while we're capturing, and any system interruption does not affect the fact that we're actually taking a data point as rapidly as the meters can function. Now, the resolution of the meters is controlled by the dwell time, the meter dwell time, and the smallest dwell time is 10 milliseconds. So that means you can have a resolution of 10 milliseconds, which is plenty of resolution for doing click measurements. So You can use the strip chart to do click measurements, and you can also use the strip chart to do a capture of data from an antenna while, for example, while a turntable is rotating, and it frees your computer from the need to keep up with that turntable. So let's, for example, say that you have a 1 RPM turntable. That means you're doing 6 degrees per second. So I would like to get more than 6 points per second, say, to make sure that every degree of rotation is captured by at least 1 point. So a 10 millisecond dwell time gives me 100 points per second, so that's plenty fast enough to make sure I have 1 point per degree. In fact, I'll have about 16 points per degree. So if we restart our capture and set our reference value back to 0 so that we're actually looking from the beginning. And now I know that if I capture for a minute while the turntable is rotating, then at the end of that minute, I can stop the capture and I'll be able to correlate the data in the strip chart with the position of the turntable in its rotation. And so I can just capture for a minute, and at the end of a minute, I can simply load the trace data with one operation from my strip chart, and I don't have to worry about my computer keeping up with my turntable. It can go and do other things while the strip chart is taking care of recording the data. And now the strip chart measurement is a spot frequency measurement. Right here you can see the frequency is 922.27 megahertz. Uh, it's recording what's happening at 922.27 megahertz. I can change the frequency. For example, I can change the frequency to 100.1 megahertz, which happens to be the frequency of an FM station in our area. And so now I'm looking at the instantaneous value of the detectors while they're tuned to that radio station. So if you're trying to capture data at a spot frequency, look at the data history or do click measurements, and you want to free your computer up from having to keep up with what's going on, simply use the strip chart measurement, and when the measurement completes or when you've captured data for as much time as you wish, you can simply offload the trace data in a single operation. And of course, as with everything else in the N6141A, you can save the trace data to a file, which will be a CSV file, either locally or on a thumb drive or on a network drive. So the strip chart measurement frees you and your computer up from a lot of the throughput issues that are associated with making measurements at a spot frequency. Now, I should say something about the dwell time control because we have been asked questions about this. So let's restart our measurement and let's take a look at the meter controls. Um, there are those who have asked, hey, if I'm making measurements like with the quasi-peak detector, don't I want a resolution dwell time of more like a second or so? And the answer to that question is, well, obviously, the quasi-peak detector responds with some lag to events in the time domain, and of course, if you're trying to make a CISPR compliant measurement of the quasi-peak detector, then you'll want to dwell for a second for sure. In the case of the strip chart, what you're usually trying to do is get an idea of the signal dynamics. So remember when we were at 922 megahertz, we had that signal that was changing really rapidly and demonstrating a lot of the value of the strip chart and looking at signal dynamics. Here we're using 10 millisecond resolution on the meters. We're not dwelling for 1 second. And so we're not taking quasi-peak readings that we would submit as part of a final compliance measurement. We're looking at the dynamics of the signal. If I wanted to set the dwell time to 1 second, then yes, each point on the display would represent a dwell time of 1 second. And I could say, okay, my quasi-peak detector. Each of these points I'm measuring with my quasi-peak detector. I'm dwelling for long enough to satisfy the CISPR spec. But that isn't the main thrust of the strip chart measurement. The main thrust is to use a high resolution, a short dwell time, and measure your signal dynamics. So if you're trying to make CISPR compliant quasi-peak measurements, use frequency scan. If you're trying to look at your signal dynamics or capture signal history, use the strip chart.